official seminar start. All right. All right. Okay. Hello, Shaba.
Hello. Hello.
Hello, Shaba. Yes.
Hi, nice to see you, Sasha.
Yeah, I cannot see you, but it's okay.
No, I have no camera because I use a big screen.
Laptop.
Laptop is always closed. So if you like, but I open that, but I lose my. Thank you for organization.
Yeah. You're very welcome. And
I'm here. I use a background of picture in the nearby.
Okay. Are you in Paris?
In files.
No, in Paris. Where you are?
I'm in Cergy in Paris. Yeah.
Okay. Okay. At home.
Yeah.
Okay.
That's not my garden. My garden is tiny. That's much bigger.
And much brighter.
Nice to see you. Yes.
Nice to see you. Okay, so we are almost ready. And
okay, I close that.
Yeah. Now, Matt, please open your slides. And may I ask all participants from now on to mute microphones and their microphones, and also to switch off cameras. Okay. Switch off camera. I'm just checking that yeah, everybody without everybody, yes, and it's a pleasure to invite. I don't know, he was already invited, but to introduce the Matt Moore from Oxford. I understand from institute, mathematical institute, right? Or yeah. We are in contact for, I don't know, 10 years or could be even more. So it's always pleasure to see Matt and to read his papers and also papers from other scientists researchers from Oxford. So today it's another hot topic is how to match air cushion with Wagner theory, and Matt will present today his vision of this story. The paper is in archive. And it's available, but also it was submitted to Journal Engineering Mathematics, and it's under processing now. So, but please, you are given, say, 45-50 minutes for presentation, and then we'll ask questions. May I ask all participants, please switch off your microphones and your camera, and I'm also going to do the same from now on. And then at the end of presentation, I will enter again and continue with the running the seminar. So Matt, the start showing full screen, and yeah, perfect. And then everything is yours.
All right, thank you very much. So yes, thank you very much for inviting me today, Sasha. So yep, as you said, my name is Matthew Moore. I'm currently a postdoc at Oxford, and I'm going to be talking today a little bit about some of my work thinking about impact theory, and in particular how we build air cushioning effects into impact theory. So just to sort of start off with a quick overview of sort of the impact theory field. So it's sort of motivated by work in the 1920s and 30s, thinking about seaplanes and naval architecture problems, where people were interested in. Hang on, let me get this laser pointer up. So you're thinking about what the forces were when these seaplanes land on the ocean. So if you can predict what the forces are on the hydrodynamic forces are, then you're going to be able to build a seaplane that won't break. So this is the sort of seminal paper for the field written by Wagner in the early 30s, where he was the first to really sort of break down this problem into what we understand today as Wagner theory. So this is a sort of little snapshot of what's going on around one of these seaplane landers. And here you have the ocean. This is the seaplane lander here. And you can see that as it lands, it's violently displacing the ocean surface into a splash. And it's this sort of really rapid topological changes over quite short, quite small length scales that really make this quite a difficult problem to understand. So what's going on here is Wagner is basically looking at the very early stages of the impact problem when you're going to get the highest forces on the seaplane lander, and he's sort of breaking the problem up into several sub-regions where you have sort of a deep pool where the seaplane looks like it's landing on the top of the free surface. But then if you zoom in locally, you get this violent displacement and this jet, which is the spritzer here. So you can see it shooting off from the body. So I'm going to talk a little bit more about the details of what Wagner theory entails in a minute, but it's essentially a sort of very simple in terms of the physics it includes. So it just includes the inertia of the liquid while neglecting things such as viscosity, surface tension, gravity, and the surrounding air. But even under all of these sort of physical simplifications, the problem is still highly nonlinear. So it's this rapid topological changes that really make it quite a complicated problem. So the general idea is to sort of exploit Wagner's thought that the forces are going to be highest early on and to really break down the problem even further. So I've just got a sort of little schematic of the sort of picture you should be having for the theory. So what we've got here is looking at half of the picture. So this y-axis is meant to sort of it's meant to be a symmetric problem about the y-axis, but this is the seaplane coming in to land on the ocean. And you can see this is the large deep pool of liquid and the free surface has been turned over. So the early time ideas are basically thinking that at the early stages of the impact, it won't have penetrated too far into the sea. So this distance here is going to be quite small compared to how much of the seaplane itself is quite wet. So you get an aspect ratio here, which is quite small. So you can think about it as an aspect ratio, but it's also a sort of early time parameter. So in the sort of language of matched asymptotics, you break down the problem by thinking about epsilon being small and thinking about different regions where different sort of dynamics are important. So I'll explain a little bit more detail later on about how this manifests itself in terms of the asymptotic structure. But Wagner theory has been a sort of successful way of modeling these impact problems. So not only solid liquid impacts, but also the sort of the converse problem where you have a liquid droplet hitting into a solid. It's been used quite successfully over the years to sort of explain and understand some of the dynamics. And that's yielded sort of a number of researches, not purely in the classical problem, but also with sort of various extensions. So thinking things about oblique impacts where the impact velocity has a tangential component. So you might think about a skimming stone where you're skimming it horizontally, but it is entering as well. Or things such as in introducing some elasticity in the substrate, so some compliance. So you're thinking about little droplets of liquid hitting onto a solid, but that solid then bending in response to that. So sort of thinking about this rain droplet hitting a leaf here. So these are sort of things you can build into sort of the classical Wagner problem. So it's of really fundamental interest to a variety of impacts. You've also got problems just involving liquid impact themselves, so things such as wave impact onto offshore structures, where the ideas are sort of similar to the Wagner problem, where you like to understand what the hydrodynamic forces are, to things such as inkjet printing, where you want to know what happens as the droplet hits the paper and whether you're going to lose any ink to splashing and things like that. So there's sort of a whole variety of different applications to the problem. But so the focus of what I want to speak out today, and as Sasha alluded to at the start, is that I want to think about the effect of the surrounding air, which has been sort of a real interest in the research field over the last few decades. So this is the sort of classical picture of what I was speaking about earlier, where we have a Wagner impact. So this is the seaplane coming in, it's coming into land. So before touchdown, it's just traveling through this essentially a vacuum, touches down at t=0, and then the impact begins, and you get this free surface being turned over into a splash. So sort of obviously that's not really true. Obviously there is a gas between this impactor and the liquid pool. And so before touchdown, you eventually get close enough so that there's the air's trying to get out the way and there's some deformation of the free surface in response to that. So what you're getting is this sort of interaction between the air and the liquid, which deforms the surface so that when Wagner says things should touch down, we actually don't have touchdown yet. We actually still have an air gap between the two, and we have significant deformation of the free surface. If you take things further and further, eventually the impactor, of course, does touch down, and you get this sort of 2 points either side of the minimum of the body where we get the touchdown, and you have this bubble trapped in the middle. So none of this is being built into the Wagner dynamics, and it's sort of interest to me and other researchers in the field about how we can sort of build that in or think about what its neglect does. What are we missing out on here? So just a sort of, that's a bit of a spoiler there. So what we're going to think about today is sort of firstly, we're going to look at when the dynamics kicks in between the air and the liquid, and then what that introduces in terms of an initial flow in the liquid. So the dominant interaction will be between viscous forces in the air and the inertia in the liquid, which leads to that free surface deformation. And sort of a number of different researchers have thought about this over the years, so people, including people who are here today, such as Peter Hicks and Richard Purvis, Frank Smith and co-workers. And what they've been looking at is this interaction dynamics. And so this is a little picture from this paper here, looking at three-dimensional droplet impacts. So what you want to be thinking about here is this is a sort of slice of a droplet coming in, so it hasn't yet been disturbed. But as it approaches the substrate down here, the free surface eventually starts to deform under the air effects, so that you get this minimum moving along the body, along the droplet down to here, and you get touchdown away from where you might expect it in the classical Wagner problem. And so lots of people have been interested in this over the years, and they've been thinking about how the aerodynamics comes in to impact problems. So the sort of the work that really inspired what I'm talking about today was work by Peter Hicks and his students a couple of years ago, where they were comparing this pre-impact dynamics, where they build in the air cushioning effects and couple that to the liquid motion, and compare that to what Wagner predicts on an equivalent timescale. So just to sort of take a picture from their paper here, where they've been looking at this is a cylindrical impactor, now a solid impactor coming down. And it splits this picture into two halves. The one on the left is the picture in classical Wagner theory. So the cylinder comes in and touches down at t equals 0, which is this dashed blue line. And you then get this dynamic as the jet grows along the side of the body, and you get the impact. However, on the other half of the picture is what happens if you keep in the air and have that pre-impact dynamics built into the problem. And you can see that at t equals 0, we haven't yet touched down. We actually have to go up to t equals 4 until we actually get touchdown of the body. So you can see there's a sort of significant difference between where the free surface profile is in the middle compared to where it would be in Wagner theory. And obviously that has built up a liquid motion in the process. So you can do similar things with other properties of the flow, such as the free surface velocity. Again, there's a noticeable difference, except possibly in the middle, which is something we'll talk about a little bit later. And things like the pressure in the gas. So this is the pressure on the surface here. So you can see what it looks like in the Wagner problem. So this is the pressure on the free surface. While with air cushioning, it's slightly different. And again, with the velocity potential, you again see this difference between what Wagner theory says is happening and what is actually happening. So the motivation of this current work is to try and sort of build in this pre-impact dynamics into the post-impact model. So don't take the classical Wagner problem, but try and build in initial conditions that let us approximate this air motion. So the outline of what I'm going to talk about is I'm going to first go into a little bit more detail of this pre-impact dynamics to get the right length scales and understand what coupling is going on and find what the solutions look like. And then we're going to talk about how we build that into the post-impact dynamics. So this is the pre-impact problem we want to be thinking about. So here I've got my solid impactor coming down vertically. I've got given the impact speed v, which is going to be taken to be constant here. And we've got an air layer between the solid and the liquid, where we have density and viscosity rho and mu. And this is the undisturbed waterline. So we want to work out over what length scale are we going to get deformation of this free surface and dynamics in the liquid. So what we start off with is our assumption we're going to take both fluids are going to be Newtonian and compressible to start with. And that means that we have sort of boundary conditions which say there's no flow through the impactor. That should be a UA, sorry. That's a little typo there. So it should be there's no airflow through the impactor. And then on the liquid air interface, we have the standard free surface conditions. So continuity of velocity and stress along with this kinematic condition. So this is the sort of, we're starting off with the problem. We're going to work out what the important physics is. So in the far field, so far away from the impact, obviously everything should decay away to sort of its quiescent state where nothing's happening. Well, if we take time sufficiently far away, we drag the impactor quite far away, and all the water motion should die away. So there's no disturbance of the sea before the seaplane gets there. So there's sort of the problem. This is the problem we want to be looking at. So we're looking for air-water interactions that occur when the air layer is sufficiently thin. If the air layer is too thick, you obviously don't get any coupling between the air and liquid motion, and the impactor just keeps traveling downwards. So when the air layer gets sufficiently thin, we are going to start seeing these interactions. So this is the body profile we're going to take, and we'd like to find this delta, which is going to give us what that interaction length scale is. So it can also be thought of as the dead right angle of the impactor when it's written in this form. So this delta is saying that we've got a sort of shallow body in some sense. So it's got, it's quite long, but sorry, what do I mean? It means that the its angle to the horizontal is quite small. Yeah, sorry, its aspect ratio is quite small. So this is what delta is representing here. So under that assumption, the important aspect ratio is obviously going to be order delta. So we're looking for interactions over a vertical length scale of order delta squared r, while it's a horizontal length scale, which is much longer than that. So if we put those into the model, we're making scalings that look like this, where we have a horizontal length scale of order delta. The vertical length scale in the air is order delta squared, while in the liquid, because it's so deep, we have the same xy length scales. So there's this difference between the y scales, which is important. The free surface deformation is on the order of the thickness of the air layer. Obviously, we want it to deform sufficiently so that eventually it touches down, and the impact time scale is then given by this delta squared over r over v here. So this is the Wagner impact time scale that we're considering here. So with these scales in mind, the continuity equation demands that the horizontal velocity in the air is an order of magnitude larger than the vertical velocity. But then continuity of velocity on the free surface tells me that the liquid velocity should look like this. So we actually have this difference between UA and UL. Then balancing for pressure. So we are going to assume that this deep liquid pool is inertia dominated. So you take the inertial scale in the liquid, and then to balance the normal stress condition on the free surface, we take the same pressure scale in the air. So putting this all together and then balancing the appropriate terms in the Navier-Stokes equations, you find that the delta should be taken to balance the pressure gradient in the air with the viscous terms in the x-momentum equation. And this gives you a delta that depends on the air viscosity, the density of the liquid, and the properties of the impactor, so its speed and its typical scale r, which is its size. And so this is, so if you want to see more details for this, I recommend going and having a look at Peter Hickson and Ross's paper, where they derive this in quite a bit of detail, and you can see where these scales come from. So under these scales, and with the following assumptions, which I've sort of highlighted a little bit already, we're going to neglect inertia in the air, which is this condition on the density ratio. You're going to neglect all inertia in the liquid. Sorry, we're going to only take inertia in the liquid, so the Reynolds number is going to be large. And we're going to neglect shear stress on the free surface and throw away surface tension. So under all these assumptions, which are reasonable for quite a wide range of problems, which we can talk about a little bit later, we reduce the problem to something that looks like this. So again, all the details have been done before, so this is sort of a bit of a replot of what's going on, but you can see that the important dynamics is the viscous dominated lubrication equations here in the air, along with a half-plane Laplace problem in the liquid. So you can see inertia dominates in here, viscosity dominates in here, and then there's coupling through the pressure condition on the interface, and you're looking to solve this problem. So if you go away and do that, you find what you expect in the air. You have a thin air layer where you have the lubrication equation, so you're going to derive Reynolds equation between the pressure gradient and the air gap thickness, which here is given by this. And while in the liquid, because you have a half-plane problem with the Laplace equation, you can use Cauchy's formula to derive an expression for here the pressure gradient. So it's related to the pressure on the free surface and the free surface acceleration. So these two equations, the Reynolds equation here and this interaction equation, derived in lots of detail in papers that I've mentioned before, so Smith and his co-workers and Ross and Hicks. So if you want to see where this comes from in a little bit more detail, I recommend going and having a look there. But these are the two equations we want to be thinking about, this Reynolds equation and this interaction equation. So just to sort of summarize that, here are the two equations. You're going to have to say that far away, the motion dies away, so the pressure and the free surface decay to zero. So this is in the far field. So this is as we move away from the impactor in the horizontal direction, while these ones are for, that's meant to be a minus infinity, but this is moving further away from the impact. So as t tends to minus infinity, we need the free surface deformation to go to 0. So what we want to do is find this touchdown time in the problem. And when we found the touchdown time, extract the sort of important physical properties of the problem. So things such as where we get touchdown. We want to find what the free surface looks like at touchdown and what the induced velocity in the liquid is at touchdown. So we have these sort of 3 things. Well, so there's sort of more than 3, but there's several properties we want to extract from the pre-impact dynamics that are important at touchdown. So this was sort of the aim of what you do when you're trying to solve this problem. And typically it's going to have to be solved numerically. So in order to solve it numerically, it turns out we have to sort of think, oops, I've gone the wrong way. We want to think a little bit about what happens for large negative time so we can initiate our numerical simulations. So throughout the rest of this talk, I'm going to be thinking about problems where the impactor is symmetric. So strictly speaking, that derivation didn't require the impactor to be symmetric, but from now on, I'm going to assume that it is. And what I'm going to do is say, if this is the body profile and t is quite large and negative, then what is the sort of the far away asymptotic solution of that impact of that system? So if you expand the lubrication equation, so equation 1, then you can find an expression for the pressure gradient Q, which tells you what it looks like close to the center of the domain. And if you move further away, you have to do a sort of an outer region to match with this inner region, and you find that this is the behavior. But it looks very similar, and indeed you can just write down a leading order asymptotic solution that's valid for all x. So this is an expression for what the pressure gradient looks like when the impactor is quite far away. So you can see it's very small. So if you were taking a cylindrical body, you're thinking about a very small pressure gradient, which you'd expect because the interaction hasn't had enough time to start off. So using this Q, we can substitute that into the sort of the Hilbert transform that was part of the interaction equation. And you can derive this as the leading order expression for the free surface profile H, which is sort of a little bit meaningless here because we don't really know what N is. But if you look, for example, on the line of symmetry, you can see how it behaves as t goes to minus infinity. So you can see it decays quite slowly. So you really need to use this as an initial condition to start off the problem. And for the particular case that we're going to concentrate most of our attention on today for a cylindrical impactor, you can actually evaluate it explicitly, and you can find that this is what the free surface looks like when the impactor is quite far away. So what we're going to do is take this solution for H that's here and this solution for Q and use that to kick off numerical simulations of the pre-impact problem. So we're going to do that by following the methodology of Peter and Richard in 2017. What we're going to do is essentially truncate this infinite domain at a sufficiently large distance, use Fourier series approximations for the 2 unknowns that we want to solve for, and then essentially use these Fourier series to simplify the Hilbert transform. So this problem greatly simplifies once you take the Fourier series, and it allows you to sort of solve it at each time step, and then iterate by solving equation 4 at a time step, then solving the Reynolds equation, and then putting that back into 4 until you converge, and then moving forward in time. So it really good numerical method because it sort of really simplifies what's going on. Simplifies what's going on. It simplifies the numerical complexity of this problem. So you're really able to cut down the time it takes to run these problems. If you were just to run the original problem and code that up, it would take significantly longer to converge. And so what we're going to do is we use this. I'm not going to show you too much details of the numerics here because that's not primarily what I'm interested in, but we're interested in what we get out of this and what the solution looks like at touchdown. So now let's go, and I think the next page will show us a little example of what we get when we solve this numerically. So this is what I'm going to be showing you here is sorry, I think someone's microphone's on. I can hear myself.
It's okay now. It's okay
good,
now.
Good. So what I'm going to be showing you here is for a cylindrical impactor, which is this black curve here. We're going to send it down towards the liquid pool. So down here, this is the ocean. And we're going to see in here, you're going to see the deformation of the free surface. In the middle, I'm showing you the sort of the velocity in the liquid scaled by its maximum. So you can see early on, it's going to be constrained up here. And then in the final one, I'm just going to plot the maximum velocity. So we can sort of see what the interaction is doing and how we're moving away from an initially quiescent pool. So I need to switch back to an actual mouse, and hopefully this will work. So the video is a little bit slow, and I apologize for that. So we are coming down to, you can see here, and this free surface will slowly start to deform. And you can see that we're starting to increase the velocity in the liquid pool as we get closer and closer. So just pausing it now, we're just after when Wagner said we would have touched down, and you can see we're still quite far away from that. And so we're going to have to run quite a little bit further, but we've already induced significant motion in the liquid. Well, significant, it's quite small at the minute, but it will build up. So if I run it a little bit further, so we can see this is going to start to build up even more. You can now see the free surface is starting to sort of sharpen here, and it's going to start rising up to meet the body. And we are approaching sort of order 1 maximum velocities in the liquid, which is happening near the point where the gap is thinnest. So I think this is going to stop at 7, so I'll stop it there. So what you see is you've now really got some significant velocity in the liquid. So you can actually run this further and further until touchdown. It just becomes quite hard to discretize the velocity plots I've got here, so I've stopped it here. But if you run it further, you're going to get touchdown eventually, and we'll see this bubble of air trapped between the body and the ocean. So just to give you a snapshot of what things look like at touchdown. So this is the free surface profile when the code breaks down. So I give it a given tolerance. So once the gap between the body and the sea becomes sufficiently small, the code stops and says it's touchdown. And you can see that we've got this bubble of air trapped between the body and the sea. And this is the free surface velocity in plot B. So on the between the air and the sea upstream of the touchdown, ahead of the touchdown point, you can see that it just decays away towards 0, while in the middle between the touchdown point and its mirror image over here, the free surface velocity is essentially uniform. It's basically -1 between the 2 touchdown points. So between the touchdown points, the air is just being carried along with the impacting body. So so along this free surface, V is equal to -1, sorry. And you can have a look at what the pressure gradient looks like too. So this is just before touchdown because it gets quite sensitive, quite close to touchdown. You can see that you get this sharp change in the pressure gradient near where the free surface is its most peaked and the air gap is therefore thinnest. So, but you can see that upstream, upstream, ahead of the touchdown point, you've got this very quick decay away to 0 pressure gradient. So the pressure dies away very quickly. So the key takeaways from this one result I've shown you, I'll show you a little bit more in a second, is that before the impact, we're getting this significant deformation. There's a flow induced in the liquid, which is order 1 when we get touchdown. So it's something we shouldn't really be ignoring. But at touchdown, you've got the free surface velocity is essentially -1 between the 2 points of contact. So it's being carried along with the impacting body. And finally, ahead of the point of touchdown, we are seeing the pressure decay away quite quickly. So these sort of things are seen more universally. So I'm going to take another example from St. Hicks's paper here. Let's go back to the laser pointer. So this is for an impacting wedge. And so it's the same idea with the picture here. The left-hand side is what happens in Wagner theory, while the right-hand side is what happens in the air cushioning model. And so you can see these sorts of things again. So particularly here for the free surface velocity, you see that at touchdown, you've got this -1, not only in the Wagner problem, which is necessary because of the no flux condition, but also in the interaction condition. So the air is being carried along with the impacting body. So what we want to take away from the pre-impact dynamics are, well, we've worked out the important physics and seen this touchdown problem coming with the entrapped air. What we're going to take as modeling assumptions into the post-impact model is we're going to have initial contact over a finite set. So between those 2 turnover points, that's the initial contact region. There's going to be a residual liquid flow and free surface deflection due to the air dynamics. So this is what we're going to extract from the touchdown profile in the results we just showed. So I'm talking about file here is HC, this blue line. And we've also got the result, the corresponding liquid flow due to the potential here. And finally, we're going to neglect the air on the free surface ahead of the touchdown point after impact. So we're just going to ignore that effect later on, assume that it's negligible. So the one thing that we haven't spoken about yet is the entrapped air bottle. So I've spoken about it a couple of times. So this VC equals -1 really wants us to sort of say, okay, let's forget about the bubble after touchdown and just imply the no flux condition between those two contact points because it's consistent with this VC equals -1. So to sort of justify that a little bit more, what we want to think about is what is the time scale of the bubble retracting? So once you entrap this air bubble between the liquid and the pool, sorry, the liquid and the impactor, it's going to retract and collapse under surface tension. So a simple model for this process has been proposed by August and Prosperetti and adapted for this problem by Jerry Marston and some co-workers in 2011. So what it's just, this gives the bubble radius over time, relating it to properties such as the surface tension, the liquid density, and the retraction speed. So with this in mind, the time scale for bubble collapse, so this V here is the volume of the bubble, we get this time scale over which the bubble is going to collapse in this problem, related to how much liquid we entrap, the surface tension, the density, and this is the Ohnesorger number for the liquid. So this is an experimental observation, this Ohnesorger number to 1/2, and it was performed by Jeremy Marston and his co-workers, but it is admittedly for quite small spheres. Whether this persists for much larger bodies is an open question, but this is the sort of timescale we're looking at for bubble collapse. And essentially, to neglect the effect of the bubble collapse and just ignore the bubble post-touchdown in the Wagner model, we just need the Wagner timescale to be much quicker than the bubble collapse timescale. So if we can justify this assumption, then we can neglect the bubble after touchdown. So as just as an illustrative example, we're going to look at an impactor of size 1 meter, impacting at a meter per second. So if you do that and plug it in, you get that the delta is on the order of 10 to the -3 meters, so on the order of millimeters, while the impact time scale is going to be on the order of 10 to the -6. I don't know why there's a meters there, sorry. That should just be seconds. Typo. So we're getting an impact time scale of 10 to the -6, and it's the same typo here. But the bubble collapse time scale is 2 orders of magnitude larger. So sorry about that. That should be seconds, obviously. So, but what this example illustrates is that clearly we have the cases where the Wagner timescale is much, much quicker than the bubble collapse timescale. So we're going to ignore the bubble in the post-impact problem and simply replace its effect by that no flux condition between the two touchdown points. So that was a sort of whistle-stop tour of the pre-impact dynamics. So just so we can start by thinking about what happens after touchdown. So we're now in the case where the body has touched down. And because I'm neglecting the bubble, I haven't drawn it in this picture. So after the impact occurs, you have these two turnover points at plus and minus d. There's a jet along the body and gives a total wetted extent of 2 CT. And what we want to do is solve the problem after the impact has occurred. So I'm just going to present the dimensionless model here. The non-dimensionalization is exactly the same as the pre-impact dynamics as we'd hoped. So we're carrying on with those scalings, and now we want to look at what's happening in the post-impact model. So this is returning to that picture I showed you right at the start. So the impact is coming down with unit speed in the non-dimensional model, and so the outer region is this region here where essentially the whole problem linearizes. So you look on the length scale far away from the impact so that the impactor looks like a flat plate spreading out on the free surface, and you solve the resulting half-plane problem in the liquid. You then have to regularize that. So if you have a flat plate on the free surface, obviously that's not truly what's going on. You've got the free surface being turned over into a jet ahead of that, shooting out from the edge of the plate. And in that region, the free surface profile is order unity in those scales, and you can see this turnover into a jet. And then finally, you have the jet itself, which is just a thin, fast jet that we're going to assume is attached to the body for the purposes of today's talk. In fact, we're not going to be thinking about the jet very much at all. We're just going to concentrate on the outer and inner problems here. So just to think about the outer problem first, in this region, essentially, these are the scalings we already had. So these are the same as the pre-impact dynamic scalings. And what we want to do is write down the half-plane problem that results from these scalings after touchdown. So we'll talk about this substitution at the top, but the picture we should be having in mind here is that we have this region between two points where the impactor itself is. So this is where the rigid body is. And ahead of the rigid body, this is where we have the free surface conditions. So what I've done in this picture is I've just subtracted out the pre-impactor velocity. So this is the initial flow in the problem, but after, so this is the flow in the problem at t equals tc, so the initial flow in the post-impact problem. And what we've got is just a Riemann-Hilbert problem here, which is exactly the same as classical Wagner, except you have these terms due to the pre-impact dynamics. So you have the velocity on the free surface, and you've got these initial conditions which say that there was some deformation before we had touchdown. So if we go away and solve this, we're going to solve it in a second. We have to quickly have a check by looking close to these turnover points that we have the same sort of local asymptotic behavior as we do in the classical Wagner problem. And so you can do that by just zooming in local to one of these points D here, which mark the switch between the rigid body and the free surface. And if you look locally and use polar coordinates, you get this sort of local local problem where you're seeking eigensolutions for the Laplace's equation with no flux through the body and a free surface condition. And this means that the local eigensolutions are of the form r to the half sine theta over 2, which tells you that there's square root bounded behavior in the velocity potential local to the turnover points, or sorry, local to these plus or minus d. And so this is sort of exactly the same as what you have in Wagner theory without air. And this is all going to go through provided that the free surface velocity at touchdown admits a Taylor series ahead of the initial touchdown points, which seems reasonable when you saw the solutions there. So we've got local square root behavior and we've got a half plane problem, and that just can be solved using standard complex analysis techniques. So this is the solution, and in this solution you can see there are two terms. The first term is what you would get if you went and did the classical impact problem, while the second term is a correction due to the air cushioning flow that is there at t equals tc. So you can use that to find out what the free surface deflection is, which is quite a long, messy expression, but it's again splits up into sort of the two different parts, the Wagner part and the air cushioning part. And you can also use Bernoulli's equation to work out what the pressure on the impactor is between the 2 points plus or minus d. So in this problem, we again have a Wagner term, which is this square root singular form here. And now this air cushioning correction, which from this minus sign you might think is reducing the pressure on the impactor, and that is indeed what it does. But we'll see that in a little bit more detail. So you can see that we just build in the air cushioning here, and it's essentially adding these correction terms to the problem. So essentially the one thing that's missing from this jigsaw here is we don't have an expression for d of t yet, and this is what the inner region is going to help us do. So locally we want to look at close to where d of t is, and this is where the free surface is going to turn over, and you're going to get the jet forming. So these are the scalings local to the inner region, so I'm not going to show too much of the details here, but you can see it's 2 orders of magnitude smaller than the outer region, so it's much smaller. But on that scale, the free surface is order 1. You also might note that the pressure itself is an order of magnitude larger in the inner region, but it's acting over a very small region in terms of x, so it doesn't contribute to the leading order force, which we'll talk about in a minute. So under those scalings, the local problem looks like this. This is a quasi-steady problem where you have Helmholtz flow, where there's a dividing streamline in the problem with liquid on this side getting forced off into the splash jet, while the rest going back into the bulk of the liquid. And so this is a picture that should be familiar to anyone who's looked at Wagner theory before, because it's exactly the same as Wagner theory. The only difference will come in this matching condition at infinity, where S of t will now depend on the pre-impact dynamics. But that's a matching condition, so the actual solution gives you exactly the same form. So you get this sort of this parametric form for the flow in this inner region, and the corresponding pressure on the body, which you're going to need to work out what the impact force is. So all of this is the same as Wagner theory, but it's the J of t here which is going to show some effect due to the air dynamics. And so this J of t, if we go back to that picture, is this asymptotic thickness of the jet as we move off into this direction. So it's this thickness here. And it has an expression which has the Wagner term is this first term, pi d over 8 d dot. But then there's again this correction due to the pre-impact dynamics. So what we want to do is go and use this solution to find what d is, so we can investigate what j of t does and what the impact force does. So to find the size of the effective contact set, you essentially have to match between this inner solution and the outer solution, and that leads to the Wagner condition. So this is the Wagner condition here. And so what this basically says is that if you look on the scale of the outer region, so there's no hats on these variables, on that scale, the free surface has to rise to meet the body at this point d of t. So you get, this is the impacting body, and the free surface has to meet it there, which makes intuitive sense and can be interpreted in terms of sort of conservation of mass ideas as well. But what this does is it gives us this expression which allows us to solve for d of t. And so for this problem, it gives you this nasty expression involving integrals, but essentially all that's changed is you have the standard Wagner solution, which this you can invert as an arbol integral equation, but now we've got this correction term for the air cushioning, which involves this in the free surface at touchdown. So while this typically is going to involve a numerical solving, going to look at what happens for small time. So again, I'm returning to this case when f of x was proportional to x to the n, and I'm going to seek a small time solution, so just after impact, to work out what the asymptotic behavior of this d of t is, this effective contact set. So if you go and substitute that into the integrals, this is the classical Wagner behavior where d looks like the square root of t, but it turns out for early times the air dynamics dominate, so this is the dominant term, and so the balance tells you that in fact the delta behaves like t minus tc to the 2/3 rather than a half here. So that is in a complete contrast to what you would get in classical Wagner theory, and that's because you're now balancing these three terms. That should be a minus sign. So this is what the Wagner solution looks like. As I said, it scales like t to the 1 over n. So now we've got this difference because we've got 2/3 irrespective of what n is. But this is essentially related to, well, I say it's similar to the behavior of a flat-bottomed body. So if you get a flat-bottomed impact problem in Wagner theory, you do get this 2/3 behavior in a D. And this is a solution from Jim Oliver's thesis, where he looked at problems involving these flat-bottom wedges and derived this early time asymptotic expansion. And so we're seeing that we get similar behavior because of that non-zero initial contact set. So we can do the same thing, but look instead for large time. So now look at t goes to infinity. And so now you can see that, in fact, the first integral is much larger than the second integral. And if you balance the appropriate terms in the Wagner condition, so these two terms, you actually retrieve the Wagner solution as t goes to infinity. So early on, we were having the air dynamics dominating and changing the behavior of this d of t, but later on, it converges back to the Wagner solution, which is what we'd hoped for, because otherwise we'd have the air effects lingering and affecting the late time dynamics. And so that's essentially what I was just saying. Okay, cool. So just to build these into, this is, I'm going to build these asymptotic results into a picture where I've actually solved that Wagner condition numerically for all of t. So this is, in this inset, you can see the early time dynamics. So the numerical solution is in gray, while the asymptotic t to the 2/3 behavior that we spoke about is given here in blue. So you see excellent agreement. But then as time increases, we gradually converge on this red dashed line, which is the classical Wagner curve. So we're moving away from when the air cushioning is important, and it's really reduced that effective contact set for D, and we're going to slowly converge to the Wagner solution. So as T increases, we get back to where we would have got if we'd neglected the air. So that's all good, but now we want to use that to work out what the leading order force on the impactor is. So if you expand the force on the body, the dominant term is from the outer region, which is because it's a large pressure order 1 over delta over a sufficiently large contact area. And you can do some manipulation of the complex variable solution to find that the expression for the leading order force on the body is given by this. So again, it splits into two terms. You have the first term is the Wagner solution, which is pi d d dot, which is the classical one. And again, you have this correction due to the air cushioning. And you might note that this V of C we were taking to be -1 along the impactor touchdown. So you can see that at least early on, we expect the force to be reduced due to the air cushioning. So again, I can do some asymptotic analysis of that right before I go into the numerical solution to work out what's happening at small and long times. So if I look at the early times, I can see that I have an expansion that looks like this. So it looks quite messy, but there are two terms here. This is a t to the minus 1/3, t minus tc to the minus 1/3 term, which has a coefficient that looks like this. And then the next term in the expansion is ordered t minus tc to the 1/3. So we might be slightly alarmed by this at the start because this force is pretended to be singular close to touchdown, but that's an artifact of the model in the sense that because I'm taking VC to be -1 between the two contact points, this is actually identically 0 within the model. And so this is the dominant term in the force. So obviously, for any real data you put in as your VC, that's not going to be exactly true. There's going to be some variation away from -1. But there's a transition from pre to post impact that needs to be considered in a little bit more detail, where it's likely lots more physics will be important. And that's obviously true in Wagner theory as well. So this is it's a slight drawback of this, but of course it's the same as we have in Wagner theory. Okay, cool. So if I then go to the other end of the spectrum and look for large T, I get exactly the same predictions as I had for the effective contact set, in the sense that we are going to converge back to the Wagner solution. So early on, the force is going to be reduced, but then as time increases, we're going to converge to the problem that Wagner wrote down years ago. And so here's a sort of numerical picture of that. So what I'm plotting here is the force on the impactor, the slamming force divided by the Wagner slamming force. So obviously the classical Wagner solution predicts that is 1 everywhere, but the gray line is what happens when you include the air cushioning. So early on, you get this very large reduction of the force, where you get good agreement between the asymptotic and numerical solutions, but eventually that starts to approach the Wagner solution. And by the time T is getting on the order of 2 times T of C, you're seeing that we're very, very close to the Wagner solution. And if you plot that as a percentage of reduction in force, we're starting off from a huge reduction early on, so the air cushioning is really reducing the force right down to less than 5% when you get to T minus TC is 10. So you're really decaying quite quickly towards the impact force that you predict in Wagner theory. So it may be that that's not the easiest thing to measure in experiments or in the lab. So one thing we can do is plot the composite pressure along the body, so that you can compare that to time series in pressure from experiments. So this is what you would get. So this is the outer solution that I plotted before. So this is the outer pressure. This is the pressure in the inner region where the free surface turns over. And this is the common contribution that we use to subtract out and make the asymptotics consistent. So if you plot that at various stations along the impacting body, you can compare what happens with and without air. So these are 3 plots going from top to bottom further away from the line of symmetry of the body. And the red line is what's happening in Wagner theory. And so you can see this peak is happening much sooner than the black line, which is what happens if you include air. But what you see is that as we move further from the site of impact, those are converging to one another. So there's less of a lag between the two. But you can actually see that the shapes are very similar. They're not exactly the same, but you're getting very similar profiles in the pressure. So these are sort of all very consistent in terms of what they're telling us, in terms of how that the air is having this effect earlier on of delaying the touchdown. Then it's also reducing the force, slowing down the spread of the contact set. But as time increases, it's dying away. So lastly, I'm just going to show you predictions of the thickness of the jet in the jet region. So we had this expression earlier, but now we've got D, we can compare what it looks like to the classical Wagner problem. And you can see that if you plot the ratio between the two, then early on, obviously the ratio is very small. And so the air has really reduced the amount of liquid going into the jet. But then as time increases, again, we approach the Wagner solution again. So we again get the significant change due to the effect of the air. Just to sort of summarize, which I realize I'm getting quite close to my time limit. So what we've done is we've tried to build in the pre-impact dynamics into the Wagner model, essentially by changing the initial conditions and making some assumptions about what happens in the pre-impact to post-impact transition. So we've solved the problem and realized that in the pre-impact problem, at touchdown, the air bubble is essentially being carried along with the body, and that its collapse timescale is going to be much longer than the impact timescale. So we're going to ignore it in the post-impact dynamics. We did that, and we were able to solve the resulting Wagner problem. So that was essentially extending the Wagner theory to something with a non-zero initial contact set. And we worked out that the air was delays and cushions the slamming, reducing the slamming force, reducing the thickness of the jets, and slowing the spread of the contact set. But all of these effects die away as time increases. So for a given problem, if you are considering one of these impacts, it depends on what timescale you're really interested in these properties over. Early on, you might necessarily have to consider what the air effects are having on Wagner theory. But if it's at a longer timescale, you can sort of neglect them and just take the classical solution as your starting point. I just want to finish off by sort of addressing some of the assumptions that I made in the model and how we might talk about them. And I think the most important one is probably about the entrapped bubble. So we sort of justified why we were going to neglect it in our model, but there are certainly going to be cases when the bubble retraction timescale is comparable to the Wagner timescale. And these are the ones that are going to be sort of the most difficult to think about in some sense, because you're going to need to track what happens to the bubble in that Wagner asymptotic structure. So one possible way you might do this is by just saying that the bubble is a constant pressure patch cavity, and then apply suitable conditions at the edges of the cavity, perhaps suitable smoothness conditions like the Brillouin-Villac condition, to solve where it is as the Wagner post-impact dynamics takes place. So in terms of a sort of picture, we get the same Wagner picture that we spoke about before, but now we have this air cavity trapped between the impactor and the pool. So that the main change will be in the outer region, where you now have the rigid body conditions here. There's no flow through the body between these 2 points, minus D and minus C. But now we have the cavity in the region between minus C and C, where you're going to impose some pressure condition and some kinematic condition and find out where this patch cavity is. But obviously that complicates the problem quite significantly. But it is sort of the natural next step of where you might go if the air cavity dynamics was important in the leading order Wagner solution. And I think that's particularly going to be the case when you're considering droplet impact problems. So the nice sort of fact that the VC was equal to -1 will not be the case when you're thinking about droplet impacts. There won't be a nice transition from the free surface velocity at touchdown to what you would need to apply in the Wagner problem, because it will go from something that is moving with the velocity to something where you would like to put no droplet motion through a solid surface. So that's not going to be a smooth transition, and you were likely to need to consider the bubble in this sort of problem. So aside from thinking about the entrapped bubble, another nice possible exception would be to not use simply the reduced model solution for the pre-impact dynamics, but actually just to use the wealth of powerful DNS software that we have out there now to take solutions of the full Navier-Stokes problem and use that as initial data for Wagner under appropriate assumptions. So provided we could make similar assumptions that we've made with our reduced model, we could take actual full realistic data from full DNS and use that as initial conditions in the post-impact dynamics. And that would really help us sort of analyze what's going on in the in the Wagner model. So I've given a sort of whistle-stop tour of what's in this preprint. You can find it archived. It should be appearing in JEM later this year. And if you have any questions about that or want to have a look, there's the link. But otherwise, you can ask me now. So thank you for listening.
Thank you very much, Matt. And the best would be to ask Matt just now. If you have questions. So any questions, please? Any questions?
Nobody else is. I will. Yes, I do.
Yes, Healy or John. It's Aiton Healy. Yes.
Thank you, Matt. Yes, I'm a bit worried about the air in this bubble. I would have thought you said the pressure gradient gets very large as you think it's going to treat it as a bubble from then on, but I would have thought the air would be wanting to rush out through that narrow gap, and your squeeze film model, that's what I'd call it, won't be valid anymore. You have inertia, and you might, and certainly compressibility, I think.
Do you mean in the really local to where it's the air is
very low? Yes, and
I think you're right there. So I think if you were doing a transition from when you're just at touchdown to the after touchdown, there's going to be all those effects are going to be important in that region. There is certainly going to be. Yeah, I agree with that. You're going to have to consider those effects.
If it was for a ship or something fairly large, I agree. If you're doing a small drop or something like that, you're probably all right. But I seem to remember some people back in the 80s in the 1980s were looking at even choked nozzle flow in that little gap.
Yeah.
Which I think. What evidence there was that you might get the compressibility was really getting very important there.
So okay, that's good to know. So this is that would be important to note. Yes.
I think we did mention that some of that back in that 93 paper.
Okay. No, I definitely agree with you.
Yeah, there are many effects involved. It's John mentioned that choking effect. There could be mixing between the air and water in close to the touchdown. Then there are no certain touchdown. It's kind of the mixing, and there the contact and could be through the layer of mixture or aerated water. Say. So it's quite complicated and difficult to understand and to decide what's going on with that. By the way, any other questions? Any other questions? If not, I can ask. Yeah, Xiaobo and Peter. So Xiaobo, you are first.
Thank you. Can you hear me?
Yes.
Okay. Thank you I learned much. Impact is not my main object. I'm wondering if I can ask a question about, of course, as you started with a plan to go glycine or drop down the water surface. So in every I learn or I see the impact problem, you consider only the vertical velocity.
Yeah. Yes, you're right.
Is there any effect of horizontal velocity or oblique? In the true world is oblique. What's the effect of this horizontal component of velocity? In general, that's much larger than vertical.
Yeah, I agree. Absolutely. And so speaking first of the classical Wagner problem, that's absolutely true. So the Wagner problem needs the oblique velocity component to be much, much larger than the vertical one for it to change the leading order problem. Otherwise, the problem remains symmetric. So once you get this sort of skimming motion, so this very oblique motion, you do get it coming in. So exactly the same will be true here. So what its importance is before touchdown is I have to say I haven't thought too much about it. Obviously, it would make the problem a little bit more complicated to solve and expensive to solve because you can't use any symmetry. But apart from that, you could certainly build it in. But I think this is something I want to consider because if you can look at what the oblique impact, the effect of an oblique velocity is at touchdown, it may be that with air cushioning included, you can induce some effect of the oblique motion even at lower oblique impact speeds as well. So even when it's comparable to the vertical velocity. So I think the answer to your question is yes, it is very important, and it's something that I certainly want to think about. And I think that the air will probably break the symmetry earlier, as it were.
Yeah, and I remember paper by Richard Purvis. It's about oblique impact, and he argued, as I remember in the paper with his co-authors, that the air cushion is more unlikely with oblique impact. So the in vertical impact, the kind of more air is trapped. But if the horizontal velocity is high, then potentially there are even no trapping air. No air cushion may happen. But the next question is from Peter Higgs. So Peter could explain more about it. Hi, Peter. Please, your question. Nice to see you.
So,
Thank you, Matt, for a very interesting talk. I wanted to ask, if you have this bubble sitting in front of your body which is carried forward, to what extent can you just consider that as a deformation to the shape of your body? Because you've kept your body shape as it was before, but if your bubble is moving with constant velocity, body shape, don't you?
Well, so yes, I agree with that. So that would, I think, be an important. So in the model that I've written down, you don't need to know that body shape between the contact points after that, right? So the Wagner condition is only being applied ahead of that where there is no bubble, so we're okay there. And I think that a next order in the Wagner problem, or at least, or it's possible at some earlier stage with local to the transition. I haven't thought about it enough, I don't think, but you're going to need that body shape change. And I think you're right. I think that needs to be included in the model at higher order. But I think within the model it is as it is. I don't think it makes a difference with the fact that there's that small perturbation away from the body shape. I don't think it changes the solution.
Okay, thanks. So just connected to that, if I can, another question, Sasha. The last you're talking about the droplet, and we know in experiments with droplets that there's pocket the air bubble. In the center of that pocket, once that bubble starts forming, the free surface doesn't go up or down very much at all. It sort of stays at the same place, and then it's moving towards the edges where the contact is happening.
Yes.
Now, is that analogous then? That's you were saying the droplet doesn't have this feature where you have the constant velocity, but we know it's sort of zero velocity for the majority of this bubble because of experiments. Is that the same thing we're seeing there?
I think so. Yeah, I think so. I do think it's slightly more. I've only briefly thought about the droplet problem recently, and I have to say I do think that there is a. I think you're right. We'd have to make an approximation along those lines. What's the word? Inspired by the experimental data. I think I think if you look at purely the snapshot of the profile from the numerical simulations, I think you see a residual. Well, you don't see it basically being zero everywhere, and so that is what worries me, because you would then have that jump from that boundary condition to no flux, which doesn't make a sense. But if we can make an experimental justification, or at least a simplification, that I think that's worth exploring. But it might be better to sort of try that with the bubble included in the post-impact dynamics from the start, just to see what's going on. Because I think getting the retraction timescales will probably be comparable there. I would have thought. I haven't looked in too much detail, I have to say. But I do think that's a good point.
Thank you.
John?
Could I just make one other comment? You sort of said the pressure peak, and the Wagner pressure peak is only over a very short time, but in fact that's what does all the damage in a lot.
Yes, yeah.
And it's very interesting if you're getting that pressure peak moving much more slowly as a result of the bubble. That's going to have quite an effect on the possible damage that pressure peak might do, because
I think so,
the ship would feel the pressure over a longer time.
I think so. I think what I'd like to do is sort of investigate these results a little bit more carefully and compare to some sort of, at least to some simulations of what we can see with sort of none of these assumptions built in, so we can sort of see that these are doing a good job. But I agree, it's the slowing down of the pressure peak is very interesting, but it's also reducing that pressure peak a little as well. So
does it? Oh, well, maybe it cancels out.
It could, yeah.
Yeah. I have a question, but technical question. You showed in one slide that VC is equal to -1.
Yes, approximately.
Approximately. So how good is that approximation?
Well, I can't. It's well, aside from very close to where the touchdown occurs, it's less. It's within sort of 5-10%. So it's very close to -1. It's less than 5, but it's the sort of the close to the touchdown where it starts to, obviously, because it has to peak up there because it's getting to its highest point. So I think that would tie into what you were speaking about earlier, and John, where you're talking about locally there's the air streaming out of this thin gap and there's more physics going on. So within the actual bit in the middle, aside from where the touchdown is, it's a very good approximation. It breaks down quite well there. But then it also relies on how good your numerics are as well. So
if it's a VC equal to -1, what is the kind of that vertical velocity, d big phi dy in the center? Is it 0?
I think, hang on, I had that. Let me.
Okay, can you show that slide with a problem for a big phi?
I can.
Yeah, it's on at the beginning.
That one, no, the next one, that one.
Yes, and that is d phi c dy. That is VC, right?
Yes, so you do have phi equals 0, yes.
Yeah, so if it's you approximate it with -1, that big phi dy is 0.
Yes, absolutely.
So in some sense, that means that there are no impact in the central part of the region, but mainly at the over here.
Exactly, exactly. So it's all coming, the perturbation, there's as if there's no impact happening here, but it's all built into this first term, the phi c.
Yeah, so the kind of impact mainly close to the contact point, in some sense.
Yes.
Okay, and this is fit the pre-impact case where main change happened also close to the touchdown point, say, the contact point.
Yeah.
Yeah, okay. Mm. Yeah. Mm-hmm. You mentioned direct numerical calculations. Do you have certain plans about that?
I'm hoping at some point to persuade some of my collaborators who do those to give me some. Doing a solid body moving problem is always more tricky than doing a droplet impact problem in DNS problem. So we have to be quite careful about how we do it. But I do plan to sort of look at how it compares with DNS, especially because that sort of help verify the sort of the pre-impact predictions as well. Although thinking about, although again, those DNS would not include compressibility, so we might have to think a little bit more about that if we want to do that.
Even without compressibility, it would be interesting to see.
I think so. I agree. It'd be very interesting.
Yeah, very interesting. In particular, if it's kind of that, I don't know which technique, is it basilisk or kind of Jerry's you are going to use? But they are, as I understand, they are tracing very well the position of the phase surface. But if you use the say other code software which allow breaking liquid into pieces, then you can find that choking effect or mixing near the contact point. So that is the Jerry's or basilisk could be kind of too fine.
Maybe
for that. So there is some physics could be missing.
True. That's true. It is worth thinking about, definitely.
In any case, it would be very, very interesting to see what the direct numerical simulations provide in this complicated problem. Because it's still not many evidences what's happening at the touchdown point. And when we approach the touchdown point, so it's still, at least I do not know what's going there.
I agree. It's such a complicated problem. You need to sort of have all these techniques.
Because as you said, it's kind of a change in topology, right? So
exactly. So we need the sort of the numerics and the theory to help each other out here because it's so complicated.
And they kind of that kind of theoretical simulations when the problem is kind of specially designed to describe that fine details of close to that point.
Agreed.
Yeah. Very good. Any other questions, please? Any other questions? Okay, not many. I see some PhD students attending, and the students, as far as I know, they are doing related things. So I would recommend them to contact. I would recommend, but I hope Matt is not against it. To contact Matt directly if they have questions, because as you can see, that is the most new level of research in this field. So that would may help in your own research. Okay. Then, if we have no questions, yeah, thank you, Shaba. If we have no questions, then we can stop the seminar. Thank you very much, Matt. And,
thank you very much for having me.
Yeah, it was very interesting how you managed to match these two things. It's extremely complicated even from logical point of view.
Yeah, well, yes, it is. Yeah.
So
anyway,
how to break your mind in such a way, how to turn it upside down, so to match such different things. Yeah.
Anyway, well, thank you very much for having me.
Yeah, thank you to all participants, and
thank you, Alexander.
Yeah, thank you, Alexander, and hope to see you next week. There will be also a presentation about analytical model of slamming, but with another twist. Could be more practical, could be another models would be involved in that. So that is the still mystery. So let's see how it will be next week with presentation from Lisbon. Yeah, so thank you, bye-bye, and we finish the seminar for today. So
thank you.
Bye, Sasha.